proposition from Apollonius's Conics. He wants to prove that any straight line drawn from the vertex of the conic surface to any point on the conic surface will be on the surface itself. This might sound stupidly obvious, why do we need to prove this? But things in mathematics can be surprisingly counterintuitive, and so it's worth proving. And the way that he goes about proving this, he uses a method called a reductio ad absurdum, a reduction to the absurd. I like to call this the Sherlock Holmes method, because in one of his stories he says that when you've eliminated the impossible, whatever remains, no matter how improbable, must be the truth. And that's how a reductio works. You take the opposite of what you want to prove and pretend that it's true. Essentially, you make an assumption. So we're going to do just that. We're going to assume you can draw a straight line, AB, and also have it not be on the conic surface. Easy enough. So assume that it's possible to draw a straight line from, say, A to B and have it not be on the conic surface. So again, we're going to pretend for a minute that that red line is straight. So now that we've made this assumption, what is the logical fallout of this belief? We'll see if it leads to anything absurd. Now to get there, we have to remember something from geometry that is kind of taken for granted in this proposition. Namely that between any 2 points, you can draw exactly one straight line. You cannot draw 2 straight lines between any 2 points. So, what is the logical fallout of assuming that this is true? Well, let's take a look at our conic surface. Now let's say A is our vertex, and the line that we use to generate this conic surface was, say, AC. As AC swings through space, generating the conic surface, at some point, this straight line, AC, is going to coincide with this brown line, AB, right? And AB is straight, and AB is on the conic surface. We have arrived at our absurdity. Because at this point, if this is true, we would have to admit that we have this brown line, which is has the endpoints A and B, and this red line, which also has the endpoints A and B, are both straight lines with the same endpoints, and that is absurd. Between any 2 points, A and B, you can draw exactly one straight line, which means our red line cannot be straight. And if it, and also it cannot be off of the conic surface. Which makes sense. That's why I had to draw it in this weird curved way. But what's important is that the straight line from A to B has to be on the conic surface, right? So the assumption that we started off with was false, which is what we kind of expected, because you know what assumptions do. And then he adds kind of a porism. Porism is kind of like other truths that follow from this proof. Namely that if you take some point inside the conic surface and you draw a line to the vertex to that point, that purple line must be completely inside the conic surface, or within the cone, as it were. And if you take some point outside the conic surface and you join it to the vertex, that blue line is going to be completely outside of the conic surface. All right, so that's pretty much it. That's the big takeaway. Any line from the vertex to a point on the surface, that line must be on the surface. If it's inside, wholly inside. If it's outside, wholly outside. Easy enough. Proposition 2 might also seem to be a bit obvious. But it's worth proving because I think it can lead to something that may be a little bit surprising and definitely worth considering. So let's say we have our conic surface. Again, we're going to have a vertex A, and let's say that circle BC is the circle that was used to generate it, right? If we take any 2 points on the conic surface, let's say D and E, and draw a straight line between them, that line will be completely inside the conic surface. And if we continue it infinitely in both directions, the continuation will be outside the conic surface. So again, this might seem kind of obvious, but let's go with it and see what Apollonius is up to. So let's just say that points D and E are chosen such that the straight line from A to D continues down to point B on our generating circle, and likewise A, E, and C lie on a straight line, and C is also part of our generating circle. So we want to say that the line DE is wholly within the conic surface. Well, if we think about the circle that was used to generate this conic surface, and we join BC, we know that BC has to be completely within the conic surface, right? Because the circle was used to make the surface, so any chord of that circle would have to be inside. So we know that the blue line is absolutely within the conic surface. So if we were to draw, if we were to draw a straight line from A to the blue line, so what EFG, let's call this H, we'll call this K. All right. So that purple line drawn down to the blue line and will intersect at point H, that line will have to go through the red line. We'll call that intersection K. Now, the whole blue line has to be inside the circle, which means that point H has to be inside the circle, which means that AH has to be inside, did I say circle? Inside the conic surface. Therefore, K also has to be inside the conic surface, but K is on the red line, DE, therefore the whole line DE has to be inside the conic surface. And then obviously if we produce it, in both directions, these parts will be outside the conic surface, which would be pretty easy to show, and he does a good job of that. One thing that I do want to point out, though, is kind of the flip side of this proposition. If we pick 2 points on the conic surface that aren't on the same half of it, if you can allow me to talk about an infinite surface as having halves, then it will be completely outside the conic surface, and then if produced, will be inside. So for instance, what if we took the points F and D and draw a straight line between them? F and D are both on the conic surface, but not on the same section of the conic surface, right? F is on the upper portion and D is on the lower portion. The line FD has to lie completely outside the conic surface, and then if produced, will be inside the conic surface. So why does Apollonius feel compelled to prove this? It seems to be pretty obvious from what we already proved in Prop 1, but it is kind of worth noting that if you have a straight line on the conic surface, it has to go through the vertex. We kind of proved that, or we proved that a straight line going through the vertex will be on the conic surface. But now we're kind of proving the opposite of that, that you cannot have a straight line on the conic surface that does not go through the vertex, right? If you have a straight line that doesn't go through the vertex, like D and E, that line cannot be on the surface. It would have to be completely inside of it. Likewise, D and F, that's a line that does not go through the vertex, and therefore must be outside the conic surface. So kind of the takeaway from this is that the only way to have a straight line on the conic surface is to have a straight line that goes through the vertex. And that, I think, is kind of cool. And that's it. Prop 2. We're going to combine propositions 3 and 4 together, and hopefully disaster doesn't happen. So the reason I want to combine both of these together is because they are both an introduction to this idea of a cutting plane. And they kind of go hand in hand, and the pictures will largely overlap. So up until now, we've been talking about straight lines and how they interact with the conic surface. We discovered in the last prop that if a straight line goes through the vertex, then that straight line will be on the conic surface, if it's from the vertex to any point on the conic surface. If the other point is not on the conic surface, it will be inside or outside the conic surface. But now we want to take the idea of a cutting plane. So think of a plane, like a big sheet of paper. And if we were to take that kind of like a knife and cut our conic surface, we would get what Apollonius is calling a conic section. That word section comes from the Latin word meaning to cut. So basically, if we take a cutting plane, what that plane and the conic surface have in common would be called a conic section. So for the simplest version of this, let's take a cutting plane and cut through the vertex. If we take a cutting plane and we cut it through the vertex, the conic section will be a triangle. Now this might, again, be pretty obvious, but let's walk through it. So if our cutting plane goes through the vertex A, and let's say if produced, that cutting plane is also going to hit the circle that was used to generate it, the circle BC, if it's going to cut through points B and C. That plane will also therefore since it'll cut through that base circle, or that circular base, it's also going to cut through that line BC. Therefore, we have three straight lines, AB, AC, and BC, that the cutting plane and the conic surface all have in common, and they share those 3 points, and therefore triangle ABC is the section of a cutting plane that goes through the axis. That one's not all that exciting, and maybe it's pretty obvious. If you take a cutting plane, you go through the axis, you're going to get a triangle. Now, if this triangle happens to go through the axis, and the base of the triangle BC also goes through the center of that base, of that circular base, we would call this the axial triangle. So think of this as the biggest possible triangle you can get with this cutting plane, right? Because if it was closer or further, if it wasn't going through the diameter, then that base would be smaller, right? Because we know how diameters work. Anyways, all right, so let's say we have our axial triangle ABC. Now, if we take a cutting plane, cut through the axis, we get a triangle. What if we take a cutting plane and we cut it like this, or parallel to this circular base, right? We're going to get something like this. We're going to get this red section, right? So this cutting plane is parallel to the base, BC, the circle BC. It's parallel, and it's going to result in that curved figure. Apollonius wants to prove that this red line, he calls it a line, we would call it a figure maybe, is in fact a circle. Now, how are we going to prove that this figure is a circle? He showed us. So if we go ahead and join DE together, and if we draw a straight line from A to the center of the circular base, be careful with this drawing. All right. Let's call the center of the base circle F. We'll call this point up here G. All right. So if we think of that axial triangle again, that axial triangle is obviously going to cut this red figure as well. And it's going to result in that straight line DE, which means that the axis, the line from A to F, is going to intersect that line as well. Again, because it's all part of that axial triangle. Now, if we pick some other point on DE, call it H, and then join GH. All right. And then if we were to join AH and produce it, down to that circular base, we'll call this K, and then go ahead and join FK as well. All right. This might seem superfluous, but give you a look under the hood of what he's trying to do. If you just come across some curved shape, how would we prove that this is in fact a circle and not something else, not a circle that's been squished? Now let's pretend that this actually is a perfect circle. Well, if we can find the center of it, nope, let's take that back. If we can find some point in this curved shape where we can draw a number of straight lines to the circumference and all those straight lines are equal, then we have a circle, right? But how many straight lines do we need? Well, if we only were satisfied with 2, I could pick this point, I could pick any point in this curved surface and draw, let's see, I would have to do it more like this. If I pick any point inside this curved surface, or this curved figure, I can draw some straight line and get 2 equal lines going to the circumference from that point. So in order to prove that this is a circle, we need at least 3 in order to prove that that point is the center. And if this is a center, and all lines going from it to the circumference are equal, then we have a circle, right? Because that's what a circle is by definition. All right, so that's what we're going to try to prove, that this red curve is a circle. We're going to do it by proving that there are at least 3 lines from point G to the circumference that are all equal. Okay, so let's get to it. Now, we said from the beginning that the cutting plane that generates the red curve is parallel to the base, which means that DE is going to be parallel to BC, and then likewise, GH is going to be parallel to FK. So what he does essentially is he goes back to geometry, to Euclid, and he proves some equalities through proportions. If you remember your geometry, if you have a triangle, and then you cut that triangle with a line that is parallel to the base, the parts of the sides and these lines themselves will be in the same ratio to each other. So this actually looks just like our axial triangle, so we'll call this point A. So I'm going to take the axial triangle and then remove it and put it here. So this is A, this is our B and C, therefore this is D and E. I'm also going to take that back triangle and kind of put it out here as well. So this is, actually we can complete this picture. We'll call this point G and F. And again, we know that F is the center of our circle. All right, cool. So then I'm going to get A, this is going to be F, and this is going to be K, and this is H. All right, not exactly to scale. You know what? Let's make it to scale. Oh, it looks like I'm a little bit off the camera, so why don't we just do that? Okay. Man, I cannot draw a straight line. All right, so this is F again. This is A again. And then this is our K. This is our G. And H. All right. So just to make sure that this is clear, we're taking this axial triangle, ABC, and putting it over here. And we're going to take this black triangle, AFK, and we're going to put it over here. And again, we've already established that the cutting plane that generates DE and GH is parallel to the cutting plane, or the circular base, which includes BC and FK. So, going back to geometry, if we have a triangle, and that triangle is cut by a line that is parallel to the base, it's going to cut the sides of that triangle that it cuts, and the cutting lines themselves are going to be proportional to each other. If you forgot about that from geometry, don't worry about it. But what does this mean? All right, so if we look at our picture here, essentially this whole line, AF, is in the same ratio to AG as, say, BF is to DG, right? So take a part of the bigger triangle and a part of the smaller triangle, then another part of the bigger triangle, and compare it to the same part of the smaller triangle. So we can say AF is to AG, right? Big triangle, little triangle, in the same ratio as BF, again, big triangle, is to DG, little triangle. Hopefully I don't have to keep writing that. And we can keep going, right? We showed that AF is to AG as BF is to DG, but we can also do CF and GE. CF is to GE, or EG, right? That's all good. But we can keep going because, again, this triangle over here is also going to be divvied into these proportions, right? We have our AF, AG, and therefore FK to GH. Oh, I'm going to do actually KF to HG. All right, cool. So, just as AF is to AG, KF is to HG. All right. Hopefully that makes sense. But basically, because of the parallelism of the cutting plane and the base, circular base, we have these proportions. A part of the bigger triangle being related to the smaller one in the same ratio, meaning they're just going to be different by scale. All right, but if we look at our original circular base, and we know that we started off knowing that F is the center, that means that BF, CF, and KF are all equal because they are all radii of the same circle. So from here, we can just be reminded that BF is equal to CF is equal to KF. All right. Now, again, going back to geometry or just proportions in general, if things are in the same ratio, but they're all equal, the things that they're in ratio to, therefore, must also be equal. So if this ratio is true, and these three lines are all equal, then the three lines that are in proportion to these three must also be equal, namely DG, right? Because DG and BF are proportional. Then the one that's proportional to CF, which in this case is EG. And then lastly, KF, which is in proportion to HG, therefore HG. Now, if DG, EG, and HG are all equal, and they all are coming from this point G in that red curved surface, curved area, then this section, DE, must be a circle, because we have generated three lines from the center, we now know that it's the center, that are all equal. And those are the criteria that we would need to prove that it is in fact a circle. Again, 2 wouldn't be enough, 3 is the minimum, but we could do this as many times as we want. Through this same process, we can pick any point on DE, right? We'll call this Z, right? We can keep doing this and prove that every line from G to the circumference is going to be equal to DG and EG. Therefore, the red section must be a circle. All right. So we have our first two conic sections. If we take a cutting plane and we cut it through the axis, we will get a triangle. And if that axis also goes through the diameter of the base circle, we call that the axial triangle. If we take a cutting plane and we cut parallel to the circular base, we will generate a circle. And we know for a fact that it has to be a circle because of this demonstration. All right, that's it.